Indu and I am going to talk about deep generative models as a part of the deep learning seminar series under the supervision of Professor J. Dinesh. So I am going to take you through the following topics in brief. First, I will start with why generative models are so important and then follow it up by building blocks of deep generative models such as the Boltzmann machines and the restricted Boltzmann machines. This will be followed by a brief introduction to deep generative models such as the deep belief networks and the deep Boltzmann machines. So to start with, generative models are more powerful models than discriminative models. Discriminative models are able to take an input from a rich high-dimensional distribution and summarize it with a categorical label. But with generative models, we are able to perform more powerful tasks like density estimation. In this problem, given an input x, the machine learning system returns an estimate of the true density px. The second application is denoising, in which given a damaged or incorrectly observed input, the machine learning system returns an estimate of the original or correct x. Consider, for example, denoising a noisy image. The third application is that of missing value imputation. Given the observations of some elements of x, the model is asked to return estimates of the unobserved elements of x. The fourth and the most important application is that of sampling, in which the model generates new samples from the distribution Px. Consider, for example, speech synthesis, in which new waveforms are produced that sound like natural human speech. So now that we have looked at the applications of generative models, let us look at the graphical modeling of some of these generative models and the training and sampling methods used. We will begin with a basic model of that of a Boltzmann machine. This shows the graphical model of a Boltzmann machine. It has two layers, a visible layer and a hidden layer. In a Boltzmann machine, all interlayer and intralayer connections are permitted. All edges are undirected. The Boltzmann machine is an energy-based model. This means that the probability distribution is defined in terms of an energy function E of x. In this equation, Z is the normalization factor. The energy function in the case of a Boltzmann machine is defined as follows: minus x transpose u x minus b transpose x. Here u is the weight matrix and b is the bias vector. On decomposition of x into the visible units v and hidden units h, the same equation can be rewritten as follows. The weight matrix is divided into three parts R, W and S. R captures the dependencies between the visible layer, S captures the dependencies between the hidden units, W captures dependencies between the visible layer and the latent layer. B and C are the bias vectors of the visible and the hidden layer respectively. The Boltzmann machine parameters, namely the weight matrices R, W and S, can be learned by maximizing the log likelihood of the training data. However, the problem with Boltzmann machines is that it has an intractable partition functions. Although it can be trained using methods like stochastic maximum likelihood and contrastive divergence, these algorithms require sampling. And MCMC sampling methods such as GIPT sampling on a Boltzmann machine is computationally expensive as each unit is connected to every other unit. Thus, a more preferred and widely used model is that of a restricted Boltzmann machine, which can help reduce these complexities. So the restricted Boltzmann machine is a simplified version of the Boltzmann machine. In an RBM, the intralayer connections are permitted, however, the interlayer connections are not permitted or restricted, and hence the name restricted Boltzmann machines. Since the interlayer connections have been removed, the energy function of the RBM is now reduced to include only one weight matrix, namely W. The RBM, like the Boltzmann machine, has an intractable partition function. But one good property of the RBM is that the inference problem is tractable and can be derived in its closed form. So now we will go through the stepwise derivation of the closed form of the inference problem. The first step follows from the definition of the conditional probability. In the next step, we substitute the probability by its form described using the energy function. Since V is a constant, all terms involving only V can be bundled to a single constant Z dash. In the next step, we expand the vector dot product to a sum of individual terms. And then in the next step, the exponential of summations can be rewritten as a product of exponentials. Here we have to observe a very important result. The conditional probability of the vector of latent variables H can be neatly written out as a product of exponentials of the individual Hj's. On normalizing the function inside the product, we can obtain the probability of occurrence of each Hj. So the only thing that remains is to normalize the probabilities of each Hj, and this can be done as follows. So the numerator term is obtained by substituting Hj equals to 1, and the denominator is the normalization term where we obtain the sum of the values when Hj equals to 1 and Hj equals to 0. Evaluating this results in the sigmoid function. So we can see that the probability of Hj equals to 1 given V can be written in a compact and closed form. So the probability of the latent variables given the visible variables can be written as a product of the individual Hj's. The closed form solution makes RBMs far easier to train and sample from as compared to fully connected Boltzmann machines. RBMs have an intractable partition function and hence can be trained using methods such as contrastive divergence, stochastic maximum likelihood, ratio matching, and so on. These are methods which are designed to confront the intractable partition function, and since the inference problem has a closed form solution, sampling can be effectively performed using Gibbs sampling. RBMs are the simplest and basic form of generative models. RBMs can be stacked on top of one another to form deeper models. In the next few slides, I will present in detail these deep models constructed using RBMs. The first deep model that I am going to talk about is the deep belief network. The deep belief networks began the current renaissance in deep learning. Deep belief networks were the first to outperform kernelized model and demonstrate that deep architectures can be successful. And these were also the first non-convolutional deep models to be trained successfully. The graphical model of the deep belief network looks as shown in the figure. There is a single observed layer and multiple layers of latent variables. The latent variables are typically binary, whereas the visible units may be binary or real. Usually, every unit in one layer is connected to every other unit in the other two layers, but sparse models can also be constructed. The connections between the top two layers are undirected, and the connections between all the other layers are directed with the arrow pointed towards the layer that is closest to the visible layer. The same closed form solution that has been derived for RBMs can be used for DBNs as well. Here the solutions are used for all pairs of hidden layers as well as the pair between the hidden and the visible layer as opposed to a single pair of layers in the RBM. Training deep belief networks is essentially equivalent to learning the weights of the three RBMs W1, W2 and W3. The DBN is viewed as a combination of three layers of restricted Boltzmann machines stacked on top of each other. Training is done using the following procedure. To train the deep belief network shown in this example, we begin by training an RBM to maximize this expectation. So we use the information from the visible units to train this RBM and get the weight matrix W1. This weight matrix is then copied to the first layer of the deep belief network. Using this RBM, We then sample units from the first hidden layer, that is H1. These samples are then used to train the second RBM, and we maximize this expectation. With this, we learn the weights W2, which are then copied to this layer of the DBN. This procedure can be repeated as many times as want to add as many layers to the deep belief network as desired. Next, we will look at how samples can be generated from the trained deep belief network. To generate a sample from a DBN, we first run several iterations of Gibbs sampling on the top two layers. This is followed by a single pass of ancestral sampling through the directed edges to get a sample from the visible layer. Moving forward, we will look at yet another deep generative model called the deep Boltzmann machine. The deep Boltzmann machine, unlike the deep belief network, has all undirected edges, and unlike the RBMs, it has several layers of latent variables. DBMs offer some advantages compared to the fully connected Boltzmann machines. This can be realized once we rearrange the DBM graphical model in the following manner. The DBM can be expressed as a bipartite graph with all odd layers on one side and the even layers on the other. This means that all the even layers are conditionally independent given the odd layers. The same holds true for the odd layers as well. Keeping in mind the bipartite structure of the deep Boltzmann machines, the activation probabilities can be written as shown here. For simplicity purposes, the bias vectors have not been specified. The only difference is that of the hidden layer 1, which has been sandwiched between the visible layer and the hidden layer 2, has to consider the dependencies of both these layers. We will briefly describe the training methods for deep Boltzmann machines here. The challenges in training a deep Boltzmann machine is that it has an intractable partition function and an intractable inference problem. So only approximate inference methods can be used for training the deep Boltzmann machines. This is generally done by maximizing the variational lower bound on the likelihood. Specifically, a mean field inference method is used for deep Boltzmann machine learning. An algorithm called the variational stochastic maximum likelihood is used for training the DBMs. Generating samples from a deep Boltzmann machine is a complex task as compared to that in deep belief networks. This is because generating a sample from a DBM requires MCMC sampling such as Gibbs sampling across all the layers. DBNs on the other hand require MCMC sampling only for the top two layers. The bottom layers use only an ancestral sampling which has lower complexity as compared to MCMC sampling techniques. So to conclude, in this presentation, we went through why generative models are important, and then we looked at graphical models of some of the basic generative models such as Boltzmann machines, restricted Boltzmann machines, deep belief networks and deep Boltzmann machines. We looked at some of the learning methods for these models such as contrastive divergence, stochastic maximum likelihood and so on. And we looked at sampling methods from these models which included Gibbs sampling, ancestral sampling and the combination of the two.